Yeah.
And then the second game was the debacle against the Bills.
All right, we're starting.
Yeah.
So hopefully you remember your related rates handout. We're going to be going through that. I think we'll just go through like the first 6 examples or so just to get you used to it. Hopefully by the 6th one, it'll be very clear what we're doing. And you can practice the rest if you want for practice, as well as the homework. So this is another very word problem heavy topic. If this shows up on a test, which this is on test 3 technically, I'll put a bonus on it on test 1, but it's technically this is test 3 material on test 2. But again, it'll come in the form of a word problem. You need to be able to recognize it, and so I sort of have a little blurb on it. The idea here, the topic is called related rates. It's section 4.1. I think. And the idea is the following. If you have 2 or more related quantities, right, so you can have an equation that has several variables in it. What you can do is we know how to differentiate implicitly, and we can differentiate an entire equation. So it turns out that if you know that quantities are related, their derivatives are also related, right? You can use the same relationship between the original variables to talk about the relationship between their derivatives, right? By just differentiating the equation. So the idea about related rates is basically that. If quantities are related, their rates are related. They have related rates. And so usually what would happen is, if you know the relationship between 2 or more things, and you know how fast one of them is changing, you can figure out how fast the others are changing. So that's the idea. So basically related rates, it's going to be the kind of problem where a situation is going to be described to you, and you're going to be told about related quantities, and you're going to be told the rate of change of one or several of these quantities, and you have to figure out the rate of change for the remaining quantities. So that's the basic idea. Given related quantities, their rates will be related. Hence the topic related rates. And you can get the relationship between their derivatives by simply differentiating the equation implicitly. ROCs, again, rates have changed. If the rates have changed of all but one quantity is known, can find the rate of change of the missing quantity. Simply by taking that equation, differentiating it, plugging it in your known, solve for the unknown. It's basically the idea. And so this, again, the applications to this would be something like, you can have a real world problem where you know that one thing will affect the other. So you can talk about, let's see, what's a nice example? I just thought of a morbid example. I'm trying to think of a happier one. Like the rate at which you're diminishing the water supply related to the number of deaths in a certain area. So if you're in this area where water shortage is a very big issue, and you can kind of measure how fast a certain population is depleting the water and how that rate of change is moving. Compare that to the depths that you have determined are related to this. And so you can sort of figure out, well, we know that if the water, the amount of water we have is decreasing at this rate, we can expect this many deaths to happen. And so we need to do something because it's getting out of control. You know? So it's when things are related and the speed at which one thing is changing is kind of connected to the speed of something else, and you need that idea to predict or anything like that. But in general, in this class, you're not going to do anything like that. Usually the problem is going to be very geometric, and I think I'll also stick with that. So we'll go through these examples and you'll see it. But the idea is, you know you're doing a related rates problem. If you're told about related quantities. So that's something important for you to know. Second, you're given the rates. You're given the rates. And this can be different in general, but you have all but one quantity. And then you're asked to find the rate of the missing quantity. Asked to find the rate. So like I said, test 3 is going to be very word problem intensive. So you kind of have to be able to read a problem and recognize along what lines you should be thinking. So we already spoke about things like exponential growth and decay, how you can know that a word problem is referring to that. You look for the buzzwords. If you're doing related rates, you're looking for this kind of situation being described, so you can decipher between one or the other. And based on that, once you realize that this is kind of the situation that is being set up for you, you know it's a related rates problem, and it turns out that we have a strategy for solving any related rates problem. This strategy will, at least in Calc 1, it will always work. So the thing is, these problems, they're word problems, and some of them can get kind of tedious. I don't think I'll ask you things that are too tedious on an exam. But the nice thing about related rates and about optimization, which we'll do later, is that it's exactly the same sequence of steps to do any one of these problems. There are some nuances here, but overall you would be following this sequence of steps in this order. And if anything here is given to you that you don't have to perform a certain step, you simply move on to the next step. So that's very nice. We actually have a method to go through. So just to talk about that a little bit, one, you need to read the problem carefully. That's always step one. I actually put that as a step. One, because you need to realize that, first of all, we're dealing with a related rates problem. And two, you're going to have to glean away the important information, like how are the quantities related? Can I have an equation that relates them? What are the rates of changes that I know? What are the rates of changes that I don't know? You have to make an assessment of what you know versus what you don't know and what you want to find. Okay, so that comes from reading the problem very carefully. Two, if it's possible or necessary, you can draw a diagram. Okay? Now the point of that diagram is to sort of help you figure out the relationship that you want to get to. But for example, if I gave you the relationship, if I gave you the equation, then step 2 is not necessary, you just move on. Okay? So drawing a picture will often give you some ideas as to the kind of equation you're going to want to set up. So if you're drawing a situation and you see, like, you know, it's a rectangle, you can know some forms you can use. Oh, area is length times width. If it's about the perimeter, it's just twice the length plus twice the width, and so on and so forth. You have some formulas ready, already bouncing around your head to apply them. 3, it's nice to have this. Technically speaking, it's not necessary for the method, but it really keeps you focused on what you need to be doing and prevents you from getting lost, because if it's a word problem, you're doing a bunch of stuff. It's nice to actually do step 3 to know what you have and where you need to get to. So we're going to write down the information that we already know, and then we're going to write down the information that we want to find. And that's going to make it easier to go through the steps because we'll be able to pick values from that step. Step 4 is to then set up the equation that relates these variables. And all the previous steps were trying to help you with that guy. Step 5 is where the differentiation comes in. You're going to be finding rates of change. So you're going to differentiate the entire equation. And step 6 is to actually plug in the knowns and solve for the guy that you want to find. So that will work with any related rates. So let's actually go through some problems. And I'll identify when I'm doing which steps so you guys can see that there's a pattern. You want to get into a groove with these guys. So we're going to do example 1 from the handout. And again, if you don't have the paper, you can pull this up off the website. But, let's just get into it. So in problem 1, it says a right circular cylinder undergoes expansion. The radius is increasing at a rate of 1 meter per second. The height is increasing at a rate of 2 meters per second. At what rate is the volume changing when the radius is 1 meter in length and the height is 3 meters in length? So you'd read that, that's step 1, read. And you will immediately identify that as a related rates problem, not because it's in the related rates handout, but you would identify it as a related rates problem because they told you the rates of change of two quantities, right? They told you the radius is increasing this much, the height is increasing that much, find the rate at which the volume is increasing. So you are given rates and you're asked to find another rate. So that tells you that it's a related rates problem. So we have read the problem and we've discovered, okay, it's a related rates problem. So we immediately know to go through the 6 steps on the first page. The second step is to what? Draw a diagram. So here, a right circular cylinder is just a cylinder with, is basically a circular prism, where we know we have a radius and we have a height. Both the radius and the height are changing, so I label them with variables. It's important when you do the diagram that you label it correctly. So things that are changing, you label them with variables. If anything's not changing, you label it with the constant that describes its value. Okay, so that's the picture. And hopefully that just kind of starts to pull up fond memories from high school geometry class. You can come up with a bunch of equations that have to deal with that guy. The idea for prisms, well, we'll get to that when we get to the formula. So that was step 2, to actually draw a picture of the situation. Step 3. Write down what you know and what you want to find. Okay. So far, what do we know in terms of these variables? What information are we given? Yeah?
Well, you know the radius is, or you can find volume from that.
Yeah, but I'm saying, what do we know in the problem? What information are we given?
The radius and the height.
Sure, but we also know rates, right? How do you write down the rates?
It's like d of r over d of t.
dr dt. This is the rate of change of r. So the question told us about dr dt, and what was that? One. Question also told us about something else, right? What else did it tell us? dh dt. It told us that the height is increasing at 2. Now, something I want you to realize that happened here, that there is something going on in the background that you sort of have to be aware of. I wrote these down as positive numbers. Now that won't always be the case. Why can I write them down as positive numbers? Yeah? Because they're increasing. So before, remember, we had this interpretation of the derivative that when the derivative is positive, it means you're increasing. If your derivative is negative, it means you're decreasing, and that takes effect here, right? So when you're writing down the rates, sign is something that you'd have to consider. So if the question were to say that the radius was decreasing at 1 meter per second, I would put a minus 1 meter. So that's important. That's why it's important to read, right? Because you're reading to know how you're going to put these values down. They're both positive numbers because we know that they're both increasing. Okay. Now, what do we want to find?
The rate of change of the volume.
Rate of change of volume. What we want is dV dt. When what happens? There's a certain situation in which we want dV dt.
When its radius is 1 meter and the height is 3.
When r equals 1 and h equals 3. So this is what I know. This is what I want to find. This is the situation under which I want to find it, right? So that's step 3. We're going to just be using step 3 to pick out the numbers to plug into our equations. It's nice to just have that written down somewhere where you don't have to reread the problem over and over. You can just have it nicely written there. So we've read the problem, realized it's a related rates problem, so we go through the 6 steps. Second is to draw a diagram. Hopefully this will have some formulas coming to mind. Then you write down what you know, what you want to find. Notice that I'm using the same variables that I used in my diagram. So it's the variables that you set up in the situation here. You're going to describe the knowledge that you have in terms of those variables. Okay? And of course here I'm saying V is equal to volume. Right? Volume is not really a variable that you can put on the figure itself, but it's what I'm talking about when I say V. Okay? Now we're going to move on to step 4. Now step 4 is to come up with the relationship that relates all the variables. And by relationship, when a math person says relationship, they're talking about really like an equation or some sort of function. That's an equation that relates all variables in step. Now, based on this diagram, does anyone remember the formula that you can get from the volume? What is the volume of a right circle? So pi r squared h. So there was a general concept that you would have learned in geometry that if you have a prism, it's a uniform prism, meaning if you slice it along an axis, the shape is always the same. Then the volume of such a shape is just the area of the base times the height. The base is a circle of radius r, so the area of that is pi r squared, the height is just h. So that is the volume. So that is my equation, that is the relationship that relates all the variables. Notice that r, h, and v are accounted for in this equation. I found a relationship between all the variables. The 5th step is to differentiate. By the way, implicitly, with respect to time. All right, we're finding rates. Rates is just a rate of change with respect to time, how fast something is moving. So let's go through. How would you differentiate V? It's derivative of V with respect to t. Yeah? dV dt. The derivative of v with respect to t is the derivative of v with respect to t. Now things get a little bit more interesting. What is the derivative of this? Yeah?
It's a quotient rule.
Quotient rule?
I mean, product rule.
Product rule?
Yeah.
Okay. So notice here, all your derivative rules still apply. The concepts that go along with derivatives, they all still apply. They are not things you can forget at this point. Here you'll notice that there are two functions being multiplied by each other. Right? R is a function of time because it is changing with respect to time. H is a function of time because it is also changing over time. And so these are two functions being multiplied by together, so we need the product rule. That is how we differentiate a product. So what would it look like here?
2 pi r dr dt.
plus dH dt over dH dt over
R squared times d. Now, where did those guys come from?
it's implicit.
Because it's implicit differentiation. So remember back in implicit differentiation, if you were differentiating something like xy squared and you wanted to find the derivative of that, remember we differentiated one, leave the other, plus we leave this and differentiated that, and we have to multiply by a y prime. Remember that when we were doing that before spring break? That's the same thing that's happening here. Because these are not just x, they're functions of the input variable t. So we don't really know what those functions are, so when we differentiate it, we differentiate the outside, multiply by a derivative inside. We have to apply the chain rule. So implicit differentiation happens here. If you're differentiating any variable that is not t, you have to multiply by its derivative with respect to t. Okay, so that's where implicit differentiation comes in. Okay? So t is your independent variable here. So just like x, when you differentiate x, you didn't have to do anything, but if you differentiated anything else, you have to multiply by the prime. The same idea will take effect here, right? And that's where all the rates come from. Okay, so now it's step 6. Step 6 is to plug in nodes. Solve for the required unknown. Now there's a little hiccup that could happen in this step, but we'll deal with that in a future, later example. Okay. So what are we going to do here? What do we know from this equation? Well, do we know dv dt? No. In fact, that's exactly what we want to find. So that guy just stays. That's dv dt equals pi is just a constant, so that's going to be 2 pi. Do I know the value of r?
Yeah.
1. Do I know the value of dr dt?
Well,
It's also plus, times h, right? What is h? Well, that's 3. Plus, here I have pi times r squared, r is 1, times dh dt, which is 2. So you see why step 3 is a nice thing to have, because you just can pick them off and plug into this equation. And at this point now, we can actually just solve it. This is 6 pi plus 2 pi. So it's 8. And technically speaking, this is volume, so technically it's going to be what unit of time was I using here? Per second? It's going to be meters cubed per second. So the volume here is increasing. Notice that this is increasing at 8 pi meters cubed per second. In general, in this class, I won't care about the units, so you don't have to write them. Just writing down the answer 8 pi is going to be okay. In physics class, units are super important. What's important is the process, the 6-step process, and that you know when to plug in which variables. As long as your units are consistent, there should be no problem. But this is basically how you do a related rates problem. It's basically how you do every related rates problem. Once you know it's a related rates problem, this is how it's going to be done, right? You're going to read the problem to recognize it's a related rates problem and pick out important information. Draw a picture if necessary. This guy will help you set up that guy. Right now, what you know, what you want to find, just so you can have these pieces of information out in the open so you can just plug them in. Come up with an equation that relates all the variables that you've described here. And as I said, a lot of times that comes from the picture. It is also possible for the equation to just be given to you, in which case you would just skip step 2 and move on with the rest. The fifth thing you're going to do is you're going to differentiate. You have to remember that it's implicit differentiation because time is the independent variable, which means if you're differentiating anything other than time, you need to multiply by that derivative. You will now end up with an equation, the relationship between the rates. The rates are related. And so what you're going to do is you're going to plug in what you know, which is neatly packaged right here, and solve for what you don't know. Any questions? So it's exactly the same process. The differences will happen basically with the picture you're drawing will vary with the situation, depends on what is described. And the equation that you have to come up with, that would be different for each problem. But in principle, you're doing exactly the same things in exactly the same order. But that's the idea. You come with a picture that describes your situation, helps you come with an equation, and you just differentiate that equation, plug in what you need to, what you know, and find what you need to find. But that process will get you through anything. Any questions? Let's do it again. Let's move on to example 2. So eventually, once you really understand how to do things, you can even write the steps themselves as shortcuts. Just write shorthands for these. They're really just memory pegs for you to realize what you're doing first, second, third. And that's kind of how you should read the handout that I gave you. You'll notice that in on the first page, in the instructions and the steps, there are some words that are in bold and there are some words that are in regular font. It's because the words that are in regular font are really explaining what the words in bold mean. So if you're just thinking of a quick way to do a related rates problem, you really only have to remember the bold words, right? What these are the things, these are the points you want to hit to get through the problem. Okay. So let's do problem 2. So step 1, read the problem. The length of a rectangle is increasing at a rate of 8 centimeters per second. The width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? So we're at the problem. We realize it's a related rate problem. Why? Because they told us how fast the width is increasing and the length is increasing, and they asked me about how fast the area is increasing. So I was given some rates and I'm asked to find another rate. So it's a related rates problem. So we move on to the diagram. What's the diagram here? It's a rectangle. And so they described to us a rectangle, so the diagram is obviously a rectangle. I'm going to label this rectangle. What do you want to label it? Let's do L and W, length and width. The variables aren't given to you, it doesn't matter what you call them, just be consistent with using the same letters. So both the width and the length are changing, so they're labeled with variables. If the question had told me the width is 5, and it's always 5, but the length is increasing, then I would write down 5 here and write down L there. Right? So when you're putting a variable, it means you're conceptualizing that as something that is changing over time. Okay, so what do we know? What rates do we know? We know the length of the rectangle is increasing at 8 centimeters. So I know the L dt is 8. It's a positive 8 because it's increasing. I know the width is increasing at a rate of 3 centimeters per second. So this is the rate of change of the width with respect to time is 3. Okay, so that's what I know so far. And we want to find how fast is the area of the rectangle increasing. So what we want is the rate of change of area, which I'm going to say A for area. At the instant when the length is 20 and the width is, technically it's centimeters, but again, I don't particularly care about it. Okay, so we've read the problem, realize it's a related rates problem, so we jump into the 6th step. Next step is a diagram. Label things that are changing with variables, anything that's not changing with a constant. Write down the rates you know, write down the rate you want to find, and the situation you want to find it in. So what's the equation that relates all these variables? A, W, and L.
A equals L times D.
Area equals length times width. That's step 4. Differentiate. What's the derivative of A? dA dt equals derivative of this.
dL dt times W plus dW dt times L.
So again, product rule. I have two functions multiplying by each other, so product rule takes effect. So I differentiate the L, leave the W, plus differentiate the W, leave the L. It's with respect to time, so I have to put dL dt and dW dt respectively. So that's the relationship between the rates. And so now I'm going to plug in all the things I know, and I'm going to solve for the thing I don't know. So at this point, dA dt, do I know that? No, because that's actually what I want to find. The point of this question is to find how fast is the area change. So we need dL dt, which I was told is 8, times W, which is 10, plus dW dt, which we see is 3, times L, which I know is 20. So this is 80 plus 60 equals 140. Technically, this is centimeters squared per second, per minute, per second. We're okay? Are we getting it? But you can see it's literally like a template. I just erased. You can literally have this template in your head about what it means to solve a related rates problem, and you're just filling in the blanks. Let's try the third example. Okay, problem 3. A 15-foot ladder is resting against a vertical wall. Suddenly and without warning, the foot of the ladder begins to slide away from the wall at a rate of 2 feet per second. For those of you who went through the review, you do realize that Batman is responsible for this. But that's how fast the foot of the ladder is sliding away from the wall. At what rate is the top of the ladder sliding down the wall when the foot of the ladder is 9 feet from the wall? So a situation is described to me. I realize it's a related rates problem because they told me about the rate of change of something and they asked me about the rate of change of something else. Second, so I know I'm going to go through this 6-step process. So the first thing I want to know is a diagram that describes this process. So what do you think such a diagram would look like? It's actually a triangle. We know it's a vertical wall, so I can let that be the wall. This is of course the ground. And there's a ladder leaning against the wall. So that's the ladder. So that kind of brings me to the fact that this situation is describing a right triangle, where this is the wall, that's the ground, that's the ladder. So let's start labeling things. What do you want to label this? The base. E. Huh? E. Okay, sure. Doesn't actually matter. A lot of people usually use X and Y because, but it doesn't matter. So I guess you would say A. What do you label this? No. 15. The length of the ladder is not changing. Okay, the ladder isn't moving, right? It's always going to be 15 feet. Now technically you could put a c here, but you'd have to realize that, oh, c is a constant, and so whenever I see dc dt over here, I should plug in 0, but students will often forget that little technicality. So to just avoid confusion in general, anything that's not changing, label it a constant. The ladder is 15, the length will always be 15. There's no reason to label it a variable, it's not changing. So that is my diagram. It ends up being a right triangle, where the hypotenuse is 15, but the length of the legs are changing. So what do we know? A here is describing the height of the ladder on the wall. B here is describing the length at which the foot of the ladder is away from the wall. And what we're told is the foot of the ladder slides away from the wall at a rate of 2 feet per second. So what I actually know is dB dt. That is positive 2. I know it's positive 2 because if I'm sliding away from the wall, the length b is getting larger, it's increasing. That's it. Now what do we want to find? At what rate is the top of the ladder? So what I want is dA dt when b equals 9. So, what's the equation here? Pythagorean theorem. So that tells us that a squared plus b squared is equal to 15 squared. So you drawing the picture of the situation kind of realize, oh, that's a right triangle. Oh, what do I know about right triangles? In terms of side lengths, I know Pythagorean theorem. That seems to be a very good equation to use. So we'll use Pythagorean theorem. Now we're going to differentiate. What's the derivative of a squared? 2a dA dt. Right. Plus, similar, 2b dB dt. 0. Now if you had put c here, you would have to write 2c dc dt here, and then people are going to, what's c? You get confused. You know when you're in a test, you're anxious, you're under pressure, you're not going to be thinking straight. So let's just avoid the confusion, write a constant down so we know that that's not something we have to worry about. It's going to be easy. Okay. So now, what we're going to do is we're going to start plugging things in. Right. In fact, I can kind of divide this by 2. So it's just a dA dt plus b dB dt equals 0. Okay, so what do I know? I know dB dt. I know b. This is what I want to find. What is a? The area is half base times height. That's not what a represents. How did you get 12?
Pythagorean theorem for the triangle.
Okay. So one hiccup that you can possibly happen in a related rates problem is that you can get to step 5 and realize you don't have all the information needed for step 6. But don't freak out in such a case. All that you would need to do is go back to the relationship in equation in step 4 and solve for the missing information. So in this case, I have b, but I don't know a, but I know an equation that relates b and a. I can simply just plug them in, right? So all I'm going to do is, we need to find b to find a. The idea is here you use step 4. Right, so by the time you get to step 6, you realize I don't have all the information I need. Go back to step 4 and figure the information out. You can solve for that to realize that a a squared plus b squared equals 15 squared. This means if I plug in b equals 9, that's a squared plus 9 squared equals 15 squared. You'll realize that a is equal to 12. Now you can either compute that directly, or you can realize that this is really a 3, 4, 5 triangle. That might be something you remember from geometry. Like if this is 5 and that side is 3, then that side is 4. Right? These are they're called Pythagorean triples. They often appear together. So the hypotenuse is 5 and one side is 3, the other side has to be 4. If the hypotenuse is 5, one side is 4, the other side has to be 3. It's always true. The nice thing about these is they're proportional, so I can multiply all the sides by the same number, and the relationship will still be the same. So notice here, if I multiply by 3, I get 15. Here, if I multiply by 3, I get 9. So 15 and 9 are both the numbers here. It means that this guy has to be 4 times 3, which is 12. And so now, we can plug in. A is 12. dA dt, I don't know. B is 9. dB dt is 2. So this means dA dt is equal to minus 9 times 2 over 12. 2 to this goes 6. 3 to that goes 2. So that's minus 3 over 2 feet per second. And by the way, that makes sense. The answer should be negative, because as the foot of the ladder is sliding away from the wall, the top is going to slide down the wall, which means the length of your A is actually getting smaller. It's decreasing, so your answer should be negative. If you didn't get a negative answer here, it means you did something wrong. That's the process. We'll finish up some examples on Wednesday. So our test is on Tuesday. Technically this is not required, but I'll put a bonus problem on this stuff. So on Tuesday we'll have a test and we'll continue this after that.